So question 11 involves an application. So when the driver of a vehicle observes an impediment, the total stopping distance involves both the reaction distance, the distance the vehicle travels while the driver moves his or her foot to the brake pedal, and the braking distance, the distance the vehicle travels once the brakes are applied. For a car traveling at a speed of v miles per hour, v usually represents velocity or speed, the reaction distance is going to be represented by capital R in feet. This can be estimated by a formula. So we have a function here. So the reaction distance is going to be the R, and the speed is going to be the V. So the input value is going to be the speed. Our result is going to be our distance. So we have this formula. So we have this R of V is equal to 2.1 times V. So suppose the braking distance is going to be B in feet for a car is given by this formula here. The braking distance is going to be B of V, which is going to be this formula, 0.03 V squared plus 0.4 V minus this 14. So we actually have two functions. So R of V represents your reaction time. So you see something in the road, you're reacting and going for your brakes. How long does it take for you to see the impediment and before you to apply the brakes? This is going to be this formula here. And then how long does it take your car to actually stop? So the braking distance. So the braking distance is going to be the distance the vehicle travels once the brakes are applied. So the total distance traveled is going to be represented by this third function, d of v, which is going to be the first two functions added together. So the reaction distance plus the braking distance gives you your total distance that your car traveled. So by finding so we want to find the distance function. So the distance function, basically what we're doing is we're just adding the 2.1 V. So we have this 2.1 V. And we're adding it to the other function, which has this 0.3 V squared plus this 0.4 V minus this 14. So notice that we do have some like terms here. The 2.1 V can be added to the 0.4 V. That should be like 2.5, I believe. So 2.1 plus 0.4 gives us then 2.5. So our new function is actually going to be this 0.3 V squared plus this 2.5 V minus then this 14 is going to be our function we're actually wanting to use. So if a car is traveling at a speed of 60 miles per hour, the stopping distance is going to be what? So we're going to be using this function up here, the stopping distance function. So we're going to substitute 60 into the problem. So we're going to have this 0.3, and we're going to replace the V with the speed, which is going to be 60, and that's going to be squared, plus then this 2.5 times this 60, and then we're going to be subtracting this 14, and that'll give us our total stopping distance. So if using a calculator, we have this 0.3, then in parentheses, we have the 60, and we square that, and then add the 2.5, again in parentheses, put another 60 there, and then subtract the 14. So notice this graphing calculator does come in handy for problems like this. So we get this 1216, so 1,216, and this distance is going to be in feet. So it's going to be our stopping distance. So if we want to interpret this distance function, stopping distance function, when we're going 60 miles an hour, these would be the descriptions that we may see. So the value indicated by DSC is the total distance the car traveled, the total distance covered by the vehicle. That sounds pretty good. The car will need the value indicated by DS6 to stop once the impediment is observed. That sounds interesting. the car will need the value indicated by DSC to stop once the impediment is observed, because yeah, this actually includes the impediment. So that sounds pretty good as well. The car will need the value indicated by DSC to stop once the brakes are applied. So remember, D actually involves two things, reaction and brakes. So that one's out. The value indicated by D at 60 is the distance the vehicle travels when the driver moves his or her foot to the brake pedal. Remember, that's only the reaction distance, so that's not the same thing. So between the first two, I think the second one is better because it talks about the impediment was observed, and that was part of the discussion up here. So if we notice, when the driver of a vehicle observes an impediment, the total stopping distance involves both the reaction distance and the braking distance. So that's what we're picking up on here, is that. Okay.